Hello guys, hello everyone. So today, little bit different live broadcast. My guest, my co-host for many sessions we did. You may know him. He's Jeff Tantsura. Jeff, welcome by the way.
Hey guys, hey Aaron, great to be. And you're not only a host, you're a friend, right?
Exactly. So guys, we have a lot of talks on the channel. You might follow them around many topics. Today, our topic will be Fast Reroute. We will discuss Fast Reroute technology.
Hello guys, hello everyone.
Yes, there is a
So
background
today,
noise.
little bit different.
Okay.
Live.
I know why. Now we don't have. Okay, Fast Reroute, as I told you, Fast Reroute, we will define it. What does Fast Reroute mean? We usually call it proactive recovery mechanism. So we will define it. There are many different ways of doing Fast Reroute, LFA, remote LFA, TI LFA. For decades, we have RSVP-based TE Fast Reroute also. We have some academical approaches. Maybe you heard U-turn, not via. I'm sure Jeff is good friend of Aliya Plus. She worked on it a
I'm
lot.
chair of routing working group. It's all it's all there. Yeah.
Yeah, basically, probably you know anymore who is Jeff. So he published so many RSCs. A couple days ago, we did another video, by the way. 8920 we discussed. He was, of course, one of the co-authors of that 8920 as well. Like we discussed OSPF extendability. You can watch on the channel. Today, we will talk deep dive, actually. Fast Reroute mechanism. We will do some architectural comparison as well. In which case we should choose which one. So you can ask any question. By the way, you are seeing two very knowledgeable guys, I think, on the Fast Reroute mechanisms, any of them. Okay, let's start, Jeff. How we will do this?
So the whole discussion was caused by Ivan Spepelniak post on LinkedIn and confusion between what LFA is versus what Fast Rehash is versus what other technologies are. So Ivan is going to post blog on his site where we kind of reconvene what this he's going to use my answer as well here. But I wanted actually to talk to you to kind of clarify what we mean when we say particular terms and how they work. So from industry point of view, when we talk FRR, it means RSVP FRR. It means the network is to run link state IGP and RSVP extensions. So RSVP provides link protection, node protection, and path protection. For sake of this discussion, we are not going to talk about RSVP. There's no reason to, beat up that horse.
But anyway, let me. Sometimes it's important to translate geek to human, like what I said on Twitter a couple days ago. By the way, I remember what Ivan shared on his posts. So in fact, I also tweet about that one. So Fast Rehash, I said, it seems that some ECMP requires LFA.
We'll go through it in details.
We will talk about that. So, but for the RSVP FRR, Jeff just said, for the link protection, node protection, we call them for both of them local protection mechanisms, and also end-to-end PET protection we have. RSVP can provide both of those methods. Of course, the other technologies which we will discuss can provide link node protection as well, facility backup, and so on and so forth. Okay, let's continue.
So the difference between link node protection and path protection, in case of link node protection, the protection is local, as Aaron said. It's usually caused by interface going down, BFD changing state to down, or loss of signal, which is interface down de facto, but faster. So what's happening in local protection, you have pre-computed and pre-installed tunnel, because if you need to reconversion control plane, you are out of magic 50 millisecond window. So what you're going to have bypass or backup facility that has some forwarding element signaling. So when the interface goes down, it doesn't go all the way up to control plane. It hits this entity in forwarding plane that switches directly to backup facility, right? So in RSVP terminology, we call this device role PLR, so point of local repair. This is where you instantiate repair. And when you merge back into your network, we call this merging point. Right?
Merging point. By the way, we are talking now active standby scenario, not ECMP yet. Okay.
Yeah, so in this case, you are not using your bypass. When you do pass protection, you're protecting whole LSP. So you're not going to switch somewhere in between. It's a tunnel, right? If you get into the tunnel, you can only get out of the tunnel at the end of the tunnel. In this case, since headend of the LSP is not directly connected, or not necessarily directly connected to the failure, it needs to be notified. Traditionally, it has been done through RSVPT signaling, which could be fine-tuned and be pretty fast. I remember in Redback days, we got it to
I think
70 milliseconds or so. So it was
session
pretty fast.
Session attribute object, something like that in the reservation messages coming back. Yeah.
Yeah, so it's a, what do we call it? It's a message that goes back to headend and says that something is wrong.
Headend should be notified, which means...
Yeah, so it will come back to me, I'll tell you.
Compared to link protection, it might be just because you need to notify the headend and the failure might be closer to tail end. So notification even might take some longer time because there is propagation delay. So it may be slower than link protection or node protection, local protection mechanisms. Okay.
So to my memory, the message is called path error with some additional details, what failed, and it's not actually, it has been years since I looked into it. But
I think it's
actually, we published the video probably a year or so ago with Ross White, I think, and who else? And I'll provide the link. We discussed FRR in details. So why pass protection is of interest? Sometimes you want your backup to be as good as your primary, meaning you are going to reserve resources. You are going to guarantee that your KPIs on backup paths are as good as in primary. So you could use your PC logic or path computation to compute backup tunnel that is as good as primary, right? When you do link protection, usually you don't. Sorry. So especially in transport scenarios, if you think about backhaul, it's important to guarantee that backup path is as good as primary. And the end result, when you signal through RSVP, signaling, you are not sharing any resources, because normally you would use SE style, so shared explicit, again to my memory, and you could share resources across primary and backup. Actually, I really need to refresh on RSVPT. I don't want to tell you stuff that's not true.
Style is one of them, correct?
Yeah.
So when we have this MBB manner LSPs, primary and backup, so maybe the post-optimal path, let's say, is different than your backup. So it might be new LSP might be created. So in this case, this can be in a couple of ways. Is one of them shared style. Okay.
So anyway, I didn't plan to talk about RSVPT for this minute.
Yeah.
Let's move on. So when we talk about IPFRR, you see the difference, FRR, IPFRR.
By the way, I didn't also know, just 5 minutes before our today's live session, Jeff joined. It's busy for the day for him. And I thought we will talk about Fast Reroute in the data center. And usually in the data center routing, we don't do Fast Reroute. We do Fast Rehash we will talk about. And I thought we will talk. Then I said, Jeff, okay, what should be the introduction? He said, okay, let's talk in general Fast Reroute, so which means a lot of things. Of course, those a lot of things, today's session will be around 45 minutes and cannot be done. Maybe a couple of sessions we will do for it. Let's continue.
Yeah, so IPFRR, there's a framework. So all this work has happened in, and still happening in routing working group in IETF. There are a number of RFCs that define IPFRR framework and define LFA and all different flavors of LFA. So let's start with LFA. Loop-free alternative is a technology that provides you alternative that is loop-free. What does it mean? When you use your alternative path, it must not lead back. Otherwise, it's a loop, right? It's mandatory to use link state protocol. Why is that? You need to be able to do SPF on behalf of your neighbor. So have full topology to see that there is no loop back, right? So in naive implementation, you could do what we call reverse SPF.
Correct. And also that reverse SPF we use in BGP optimal route reflection, guys. Okay. Same logic.
So LFA can provide link protection and NOT protection. There are a number of equations that must be met in order to promote a interface to be a backup zone. So it's protecting interface to a protected interface. The problem with LFA, it's topology dependent. So I'm going to draw some stuff and show you.
While you are
actually, let's talk about RLFA and TI-LFA, and then I'll go and draw.
Yeah, sure. RLFA, remote LFA, TI means topology independent.
Topology independent. So as we said,
by the way, topology independentness. Some people may not familiar with these terms, by the way. Topology dependent mean maybe your physical topology is ring-based, partial mesh, full mesh, somehow some architectural physical topology you have there. Also, you have some cost assigned on those links in the topology, right? So some Fast Reroute mechanisms work on some topologies quite well, and some Fast Reroute mechanisms really have hard time on some topologies, guys. For example, ring topology usually, we say, harder for the Fast Reroute mechanisms than other topologies. Okay, let's continue.
So since RSVPT predefines the path, it can solve all topologies, but potentially very inefficient. So again, we're not going to touch it, but RSVPT in rings is it's very inefficient technology. So LFA requires your neighbor to be loop-free.
It seems really long topic, because when he says something, RSVP might be really, especially in the ring topologies, might be quite inefficient, because your merge point can be at the end of the world, and from that merge point you need to come back to the primary LSP for the destination, and really you might do hairpinning, a lot of hairpinning, so you might consume unnecessarily some capacity, so you don't want that. Okay.
Yeah.
Are you sharing something? Because on the screen we don't see that.
Orhan, you seem to be very active today. What did you eat? A lot of sugar?
No, I just slept very well. By the way, are you drawing something, because we don't see anything?
No, I'm not. I'm talking. I'm trying to talk at least.
Okay. Sorry if I interrupted. Okay.
Yeah. So remote LFA was intermediate solution to that problem. So what remote LFA gave us is ability to have not that merges not directly connected. So in LFA, your neighbor is directly connected neighbor, right? If it leads back to you, there's no LFA. Simple as it is. Remote LFA could be further away, and probably for another meeting, but we will go into discussion about what is P space, what is Q space, what intersection means. And for now, so you need to make it to PQ space, which is a device from which route to the destination is shorter than route back, meaning you're not going to loop back. So remote LFA would compute this node that is further away than one hop and give us ability to tunnel traffic to this node, right? It is quite complex technology on itself. Moreover, in order for LDP services to work over it, you had to establish the transport LDP session to exchange label, because otherwise, when it receives labels, top label is unknown. So in order to understand what's been received, besides computation on PLR to compute the PQ node, which is your merging point, you also need to establish TLDP session between every node you are protecting and every PQ node. So complex, had been implemented and deployed, but I mean, it was kind of workaround, right?
It was, and I know some people tried to use, and then I think that vendor actually buggy, and they removed anyway.
Yeah, but Cisco implemented, Juniper implemented it. I don't remember for Nokia. Then segment routing came around. So segment routing gives us ability to compute a path that's source-based, meaning every intermediate node will just ignore shortest path metric and just use segment routing seeds when they looked it up. If it needs to override shortest path, you could always use adjacency seed to go someplace where you wouldn't go according to your IGP. And this is exactly how TI-LFA is implemented. So probably now it's a good time to go into drawing.
Okay.
One-time drawing is better than 7-time set.
Yeah, TI-LFA, by the way, those two protocols, TI-LFA as well as RSVP-based TI-FRR can provide us 100% topology coverage, guys, okay? But there are lots of differences between them. Anyway, maybe today, maybe next session, we can continue.
You should be able to see my screen, right?
Yes.
Okay.
So what is this? Neural network?
Almost.
Almost, yeah. Hidden layers. Yeah.
Yeah, so let's take RCPT.
Okay.
So if you are trying to protect this node, you could protect through this path, right? So have it simple. So you'll compute your primary path here and your backup path around it.
And we call it also NNO protection, next door protection. Okay.
So we're not going to go in details here, but this is practically how it works. You can also protect this node. So if you want this tunnel to be not protecting, you need to find a path that is not going through this node. So in this case, again, it's going to be from here like this, right? So let's take LFA. Let's clean it up for a second.
By the way, this is called node protection, okay? Link protection, basically, the first and second node, for example, the link between them failed. Let's say. And in real life, link protection is more common than node protection because link failures are more common than node failures.
Hello, drawing.
Yeah.
Yeah, now it does. That's weird. Let's try again. Why is it ending? Show. Shouldn't. Okay. Yeah. So same network.
Mm-hmm.
So now we are going to assign cost because LFA, as we said, topology dependent and uses IGP costs to compute loop freeness. So in this case, what you see is an ECMP network, right? So in order to get to destination, you've got cost of 2 this way, cost of 2 way. So what happens if this link goes down? And this is your secondary interface. So in a CMP case, you would choose it and get here. So what's important here is total metric cost to the destination. If I want to get to destination through this link, the cost is 1. If I want to get to the destination through this link, total cost is 3. So it is an LFA, it's working, and this interface could be protecting that interface and other way around. Now, small change.
By the way, in that network, the source can do the ECMP because every top pad and bottom pad total cost is 2 to ECMP. So even if you have LFA, you will automatically do IGP protocols automatically will do ECMP, which means both of those IGP next up will be placed in the routing and forwarding table as active node.
And they will protect each other.
Yeah.
So we've just changed cost here from 1 to 4. So let's do the calculation again. We get here, and now in order to get destination, my cost going straight is 4, going back, total cost is 3, meaning it's a loop. So anytime I get here and my IGP hasn't converged yet, I'll go back. In this case, there's no LFA. So this is the topology dependency. It really depends on your IGP structure. There's been a lot of research. Typical LFA in typical service provider network will provide somewhere between 60 to 70% coverage.
With LFA?
Yes. So remote LFA is not interesting because it's not used anymore, not deployed. Let's go to TI LFA. So exactly same network, same cost. As we said, we are trying to protect this guy. So, and in this case, as you could see, the protection is not protection because we are not going to hit this node anymore. And it's an explicit computation. Usually when you configure LFA, you ask, I want link protection, I want node protection. Some vendors give you the ability to say, I want node, but if there is none, I would still like link. So as we said, if we just use IGP metrics, there's no LFA, it's not working. If we use the ILFA, however, we can use adjacency seed here. So what's going to happen in this case, our label stack or seed stack is going to be get to this node and then use adjacency seed. And adjacency seed in this case is going to override IGP decision to send it back because we don't look up. When we see adjacency seed, we blindly copy traffic or send traffic to the interface where adjacency seed is. So without looking up IGP cost, we'll just send traffic towards the destination. So TI-LFA, from this perspective, completely addressed any asymmetrical or pathological topologies, such as ring, for example, and gives you ability to always reach the PQ node. So again, we'll discuss what P and Q spaces are another time, but this is in principle what TI-LFA does.
Always reach to destination. So even if it goes to PQ node, after PQ node, anyway, PQ node is mean, when you go there, you will be able to anyway go to destination. By the way, this, as Jeff said, provides 100% coverage. And in most cases, there are corner cases as well. Most cases, I've seen 100%, but most cases provides also post-optimal convergence path. Let's discuss this one later on.
Absolutely.
Probably. Because
I mean, it's worth mentioning. So you might have more paths to do, right?
Yeah.
So
and
what?
Go ahead.
Thank you. So what it means is that the TI-LFA protection path is going to be computed based on post-convergence IGP view. So what it means, at some point, your IGP will converge and you will move back to shortest path. If you have more than one links here, you might be choosing one that is not how post-convergence path is going to look like. What it means, you will switch within 1-2 milliseconds to backup path, but when your IGP converges, you will switch to post-convergence topology, which will result in some packet loss and instability in the network. So what TI-LFA algorithm does, it looks at post-convergence topology or computes it, emulates it, and chooses TI-LFA path accordingly. So when your IGP converges, there are no changes in network anymore.
So basically what we are saying here for the post-convergence optimal path, guys, all these FRR mechanisms are data plane convergence mechanism, we call them, right? So still control plane convergence has to follow this data plane convergence mechanisms, which means when control plane finishes its job, it might find more optimal path than your data plane path. And then you need to use that control plane path anyway. And Jeff is saying, when you switch over from data plane to control plane path, you might see you might see some packet loss. In fact, you might see some weird behaviors, yes. But there are even some avoidance mechanisms for that. Let's not discuss again here.
So
like order sweep approach and many other things there, but let's not here.
So what we discussed before are technologies that require support from protocols, require support from hardware, and are technologies defined in ATF. There are RFCs for all of them, and they require interoperability because there's extensions to IGPs, there are definitions to RCPT, and it needs to be interoperable. So last topic is Fast Rehash. Fast Rehash traditionally used in data center. So you'll see it on data center silicon such as Trident and similar. So I know Trident supports it for sure. Others probably do too. So what does it mean? This is our data center. So leaf connected to number of spines.
Guys, listen here carefully because you will not see this kind of things on internet easily.
So in leaf spine network, let's assume it's BGP for simplicity. So there are no metrics, right? You use IS path as your metric, and all endpoints are equidistant. So you can always ECMP. So the more devices you have here, the wider your ECMP bucket become. So we know that ECMP is per definition loop-free. It's as good as primary. Because if it would not been loop-free, it wouldn't be ECMP. So it's safe to assume that if this link goes down, you will be sending traffic this way because you're already sending it, right? So when you go towards destination, you load share per flow. So you take a flow, you hash it to every link separately. So obviously we are not using a CPT in data center. It doesn't make sense. We are not using LFA because LFA is needed in non-ECMP topologies. We know that ECMP link is good. So there's no reason for this additional computation that requires control plane computation, which sometimes resource intensive, depending on size and some other things. And there's no need to validate anything, really. So what needs to be done for fast convergence is what we call Fast Rehash. It's an internal mechanism to silicon. So normally, imagine you have only one link. You would have a forwarding entry saying, if you go towards destination, this is your next hop. Now you have 4. Without Fast Rehash, you would still have 4 entries in your forwarding table. With Fast Rehash, you're going to have 1 entry towards destination and indirect entity here, which points not to every link in separation, but to an array of next hops. So if we have 4 links, you'll have 4 entities here. Let me clean it up and redraw.
So is this what Ivan was mentioning about next hop groups?
Yeah, so next hop group is an implementation in FRR Donald did to address exactly this scenario. It disappeared.
FRR, by the way, in this context is free range routing, I think.
Yes.
Okay.
Funny enough. So what's happening here? I cannot get. Come on. Yeah. What's happening here now? You've got forwarding structure from your PowerPoint doesn't like me today. You've got forwarding structure that looks like this. Your destination and all next hops to the destination. When I get packet that goes towards destination, based on my hashing, I'll choose one of them and just go to it. So what happens with Fast Rehash when this link goes down? I'll remove this next hop from total array. I'm not going to reconverge. So next time when I hit the structure, it will just hash traffic across remaining next hops. And it will also take traffic that was hashed initially in this bucket and rehash it again across existing next hop. So there are 2 implementations. The earlier one would disrupt all the traffic and do complete rehashing, which is obviously not good. Newer implementations do what we call sticky rehashing. So every flow that was going here will stay exactly where it was. Only new flows are going to go into this left bucket. So this is what Fast Rehash is. It doesn't require any additions to control plane. It's local to the device.
Okay, let me just tell you what you just said. So let's verify. So either sticky or old approach, you were saying for each and every flow, it was doing the rehashing. But newer approach is basically for the established session, let them continue whichever path they are basically mapped. But for the new flows, they will be rehashed. Is it correct?
So this is very fast. It happens below 1 millisecond. And
okay.
it's a great technology. Yeah.
This is great. And you are saying this is silicon job. So whichever vendor is basically using this silicon, those vendors implementation, we will see this one.
Yeah.
Great. One more question actually on this one, Jeff. Actually, there might be many questions even from the, by the way, participants. We can get some questions. We have still some like 10, 15 more minutes. For this one, Jeff, Ivan was saying some vendors, actually iOS XR, let's talk about it because he also published on his talk. Of course, I will not ask the detail of iOS XR to you, but he was just saying for the iOS XR, I think it was requiring LFA, even for the ECMP paths, to do the what ECMP's job. So basically doing the rehashing, what I understood, doing the rehashing, LFA is required, what he was saying. Do you think it is necessary also? It might.
So you need to look at Cisco perspective, right? So number one, iOS XR is not meant for data center. Never was. It's a service provider feature set. So if you look at what Cisco is doing data center, it's predominantly NXOS and some iOS XE.
Mm-hmm.
So the fact that it's not there, it makes sense from market perspective.
So you mean
it's not meant for data center.
I got your point. So for the iOS XE, we wouldn't expect this behavior, and we would
iOS XR.
No. For the iOS XE, we wouldn't expect this behavior then.
iOS XE is unclear because, as you know, the control plane part is still old good iOS, the trans daemon, and the rest is different. NXOS is an OS that explicitly targets data center. So
then for the NXOS, maybe we can say Fast Rehash might be there. And we
so let's ping Lucas Krattinger, another great friend, and actually ask. Yeah. But I would expect something like Nexus 9K to support Fast Rehash.
Fast Rehash. So basically, this brings to just reminded me another question today I got from one student. So based on what you are selecting the routers or even products or technologies, the requirement, based on the requirements. So great answer actually just provided. Okay, for iOS XR, what's the expectation? Are we really positioning that router for the data center? And this Fast Rehash, where you would use this? Where you would basically have lots of ECMP paths and divert from one failed link, those traffic to the remaining links in the data center. And Cisco's answer, position device, there is NXOS, and expectation, his expectation, and probably that makes sense, from NXOS, not iOS XR. And iOS XR still might require this LFA internally, and probably XR guys can answer.
I cannot imagine running iOS XR in data center as a switch. There's no such device to do this. And again, from this perspective, I understand Cisco position. I used to be in charge of feature set at another vendor, and even so, we usually use much more capable silicon on service provider class devices. So what does run iOS XR today? It's ISR 9K, it's long dead CRS, and what else? The new 8Ks, right? So I'm not familiar with the new devices, but
me too.
Anything that runs Jericho are actually
this is silicon, yeah.
Yeah, so capable silicon, you could easily do Fast Rehash. The question whether it's worth putting this effort into device that will never go into data center.
By the way, do you remember I referred this term to, I think Nicholas it was, on Twitter, and he was asking some official resource, official document from us. I think still there is no IETF document which is defining what is Fast Rehash. But
so there's a question I'm trying to parse ECMP group in Fast Rehash. It is ECMP. It's grouped because it is ECMP. So it is absolutely ECMP. You need your control plane to confirm that the group is ECMP, because otherwise there might be a loop, right? So if another path is not ECMP, we go exactly into LFA. And this is what LFA does in non-ECMP scenarios. It takes another path that is worse from IGP perspective and computes, looking at the LFA equalities, whether it's going to be loop-free. So ECMP group in Fast Rehash, it is absolutely ECMP. The load sharing is done based on the hashing algorithm, usually 5-tuple, could be something else. Usually it's configurable on vendor boxes.
I think you said something about NCS, so Boris is asking that.
Yeah, so I'm not going to go into propaganda about debuffering, right? NCS 5500 is Jericho-based.
By the way, did you say deep buffering?
Yes. So, don't get excited. We're not going to discuss it now.
Yeah, let's not do that, but maybe someday we discuss about buffer bloats and those kind of things. And
so NCS is IOSXR based.
Yeah.
Meaning it's not really data center feature set. It's Jericho based, meaning it's reasonably expensive. And again, the only reason to deploy Jericho today, and probably Arista would love to tell you why we need to do it, is when you have workloads such as Hadoop, so in cast, when you need buffering, and when you switch from 10 to 100 gig, so really DCI gateway or border leaf scenarios.
By the way, he said incast, which means many to one.
Yes. So otherwise, switches with shallow buffers would perform better. Yeah, I don't want to go into this discussion because it's kind of poisonous, but
anyway, we always
so I would say NCS 5500 is not very suitable for data center switch. It is very suitable as DC gateway, but it's completely different position, different market.
Any other question, guys? By the way, for the Fast Reroute today, so it's not Ask Me Anything session. Maybe some days we do that AMA, Ask Me Anything, so you can ask a question from any domain, but today let's do it for the Fast Reroute, Fast Rehash, what just you understood. We have like 5 more minutes. You can come up with your questions. Jeff, meanwhile, while we get some question maybe, let's talk something about whatever.
Yeah, so what's important here, we are talking about underlay, right? You should always remember all these technologies are meant for underlay, so it's really protection of physical resources.
So let's
your links, overlay protection, or things that are known as BGP Fast Reroute or BGP peak or BGP indirection. They're a very different set of technologies that work on top of that. And would be really good discussion for another podcast.
Correct.
I have my slides from 2013 when I was running the stuff at Ericsson Redback. So actually we could use the slides and discuss what do you need from BGP. So you need more than one next hop for every route, right? And classically BGP will give you only one next hop. You need indirection because you would have relationship between single next hop and potentially millions and tens of millions of routes.
Actually, this indirection almost like what just you explained for the next hop groups. With the Fast Rehash discussion, guys, same idea. So we have hierarchical FIB. So we have a couple different types of FIB architecture, right? So flat FIB, hierarchical FIB, generalized FIB. This hierarchical FIB, which means indirection, Jeff is talking about.
Man, don't sell at Cisco. So there are different ways to do it, and I find the way we did it in Ericsson much more elegant than what Cisco did, but personal opinion.
Let's definitely talk about that in one another show. By the way, this generalized FIB and hierarchical FIB from the IETF document, I remember.
Yeah, so there is informational document from Cisco, which is in routing working group, obviously, that talks about BGP peak. So it in high-level details explained what Cisco did to implement BGP, prefix independent convergence. I would really advise you to reading it, and it's a good document.
Another question?
So fast rehashing algo, obviously I cannot point you to Broadcom NDA documents. Try Google for it, actually. I don't remember. I used to have access to a lot of internal stuff for a very long time. It might be all in there. I don't really remember how I know this.
This question might require a lot of time, by the way, but a very quick answer we can give for this one as well. So not better. There is no better, by the way. There are some characteristics of leaf and spine, and traditional, I think you are talking either 2-layer or 3 layers, so access distribution core, etc. So there are some characteristics. So leaf and spine, equidistance topology, number of ECMP usually high, so you don't connect leaves. So there is no shortcut between leaves and spines. So there are some other stuff. Jeff, you want to answer also?
Yeah, let me do some marketing for myself. We went in details in this discussion with Jeff Doyle in Between Two Nerds. It was one of the first podcasts. So look up on YouTube for Between 0x 2 Nerds. Sorry. You will find this discussion how to address it, how to do proper ISN allocation, everything you need to understand data center routing architectures. So you get all the answers there.
Guys, it's on the Upstra's YouTube channel also. If you just click on Upstra, let me type here, Upstra. Okay, so
if you're looking for more academical answers, there is a bunch of papers by Google mostly. So they were the first to publish it in 2012 or so. So look it up. Look up for Jupyter white papers. They all talk about why leaf spine, why Google did it, and it's a great source of information.
So yeah, also Russ did one podcast with the Google, one of the guys from there, Rick, I think. So
yeah, it was very good podcast.
Yeah, you can listen to that podcast as well. Another last question. Let's get that one. Or if we have, we have 3 more minutes, guys. Why we are focusing on SS solution in SD-WAN nowadays? Let's not do it SD-WAN today. Another day, guys.
Practically, it's a new term for old thing, and you need Wi-Fi 7 and 6G to sell stuff. That's pretty much it.
Okay, for the Fast Reroute, you can still type your questions when we publish this video, when you see that. And anyway, I will be answering your questions. And if you need something from Jeff, I will ping him whenever he has time, so he might be answering as well. And probably next show might be still related with this stuff or something else. Please, if you want to watch next time live as well and ask questions to us, you need to subscribe to this channel so you will get the notification, live notification. Also, if you like the video, I think for the Fast Reroute, especially for this Fast Rehash, there is no, as far as I know, there is no other resource that you can find. So people might.
I'll look it up. So for anything that's IPFRR related, I would urge you to go to Routing Working Group page in ATF. You'll find there's in total 6-7 RFCs and drafts that describe really good details. They're well-written documents, and you will get scientific understanding of how things work. How do we compute loop-free alternative? How remote LFA solves some issues? How TI LFA solves most of the issues? So do go your reading. I mean, there's nothing better than reading RFCs, especially those that are well-written.
Yeah, well-written is, I think, an important keyword, because I find a tweet for this. So sometimes when I just read the RFC and write something about those RFCs, and also sometimes when I talk with Jeff Tantsura, I am feeling like I am a translator from geek to human. So that's the idea, guys. It was really good discussion today. Hopefully, as I told you, just like this and subscribe to channel. You will get the notification next time when we deep dive another technology, or maybe continue with this technology. You will get the notification whenever you have a question. Please ask. Jeff, let's close today's session. What do you want to say?
Cool. So thanks for being here as usual. And it's a fascinating part of routing. It requires good understanding if you're an architectural role, because one of most important things in networking, that network should work no matter what. If it doesn't, you're really screwed. So fast conversion gives you ability to converge before your applications are actually noticed. All the technologies we have discussed now outside of RSVPT pass protection are sub 10 milliseconds. So it gives you ability to switch to backup before anyone else actually knows. So understanding how to properly deploy those is fundamental to building good networks.
Okay, thanks, Jeff, for that. By the way, guys, don't forget, not every network requires 5, 6 nines availability, but not every network requires fast convergence or fast reroute with these protocols. Know your requirements, know what's your business goals, know your application tolerance, lots of stuff. Then if you come up to conclusion that you need ECMP or fast reroute, learn these technologies, because there are many of these technologies, and you need to do the trade-offs, and you need to know these technologies well to make the trade-offs, and hopefully we can help you if you ask the question. We are both using LinkedIn, by the way, LinkedIn and Twitter. We are using, so you can just follow up Orhan Ergun and Jeff Tantsura, and bye for now.